Alrighty, so in this section, I want to talk a little bit about the standard enthalpy of formation. It looks like this. So you would write delta H, and there would be a little F there. And the F stands for formation. And as we discussed earlier, the H is enthalpy. So you could say delta, enthalpy of formation. The other new part to this, besides the little f, which is, keep in mind, it's really different from delta H of the reaction. So be really cognizant of the subscript. Is this little circle up here that looks like a degree sign? It's not a degree sign. If you want to pronounce it verbally, you would say delta H naught. But that naught, whenever you come across it in thermodynamics, it refers to the standard state. So enthalpy values will change depending on the conditions, depending on temperature, depending on pressure. So when they publish tables, a lot of times they'll use what's known as the standard state. It's different from STP. So if you've done any gas law stuff and you've heard a discussion about STP, standard state is slightly different. So for a gas, your standard state is going to have a partial pressure of 1 atm, and there'll be a temperature of 25 degrees Celsius. I think scientists use 25 degrees Celsius as the standard temperature because it's relatively close to room temperature. Room temperature is usually not that hot, but it's close enough, and then it's also an easier number to remember than something like 22 or something. 22 degrees Celsius might be closer to room temperature, but that's kind of hard to remember. So 25 degrees Celsius is your standard temperature. Liquid, it's going to be very similar. Liquid will be a temperature of 25 degrees Celsius, and the pressure should be 1 atm. Because things can change even for pure liquids if you start changing vapor pressure. Solutions. So the difference between a liquid and a solution, right? A liquid is going to be pure, like water or ethanol, if you can have it pure. A solution is a mixture, so aqueous sodium chloride, for instance. So the main restriction here is that you want it to have a concentration of 1 molar, and then the other things would naturally apply as well, the 25 degrees Celsius and whatnot. All right, so now that we've defined the standard state, and that'll be your tables that you'll be using on the homework, or you could reference tables online. Most of them are under standard state conditions. You'll notice when you start looking at those tables, there's some, I have like a segment of a table on page 11. You'll notice that there's a bunch of zeros. So they had to start somewhere when they were trying to figure out the enthalpy of formation values. So it's a very adjustable scale, or maybe that's not the right way to describe it. What I'm thinking about is temperature. Temperature, we said, scientists at some point said, well, 0 degrees Celsius is going to be the 0 point is equivalent to the freezing point of water. That's kind of like an arbitrary assignment. And then 100 degrees Celsius is the boiling point of the water. But they could have just as easily developed a thermometer that was based on the freezing point of ethanol and the boiling point of ethanol. So the 0 value on a lot of your measurements or your scales is an arbitrary assignment. And it's the same thing here. We have a bunch of 0 values, and when the enthalpy values were developed, they decided that things, elemental things, so oxygen, hydrogen, bromine, solids like carbon, sodium, anything that's elemental in its natural state at room temperature, 25 degrees Celsius. So oxygen gas, hydrogen gas. Bromine is actually a liquid at room temperature. Solid carbon, solid sodium. So the way we would find it on the periodic table, if I asked you, well, what's hydrogen? You'd say, well, it's a diatomic gas. So in its natural state, those were all given 0 values for the enthalpy to kind of start off the scale. One interesting thing to take note of is there's 2 versions of solid carbon, right? There's the solid carbon that's in your pencil, graphite, and then there's also solid carbon in diamonds, and they're both pure carbon. So this one is even further defined, but you don't have to know that. It's just something interesting to think about. The 0 value was given to graphite. So if you look up the allotrope, if you look up diamond, it's not going to have an enthalpy value of 0, even though it's still solid carbon. Alrighty, so also on your table, you have enthalpy of formation values for compounds. So how did they come up with those values? So for instance, one of the ones that's listed there is ammonia. So when we consider it, we can write what's called an enthalpy of formation reaction. The target, the ammonia, would be a product. And this isn't on page 11 formally, but there is a homework question on it, and it's potentially something I may ask in the quiz. So this is what we need the enthalpy of formation for, and we don't want any other values to get in the way. So when you're writing an enthalpy of formation reaction, you want to put your reactants as things that have known 0 values, so that the only thing you're measuring is the heat associated with forming this compound. So for instance here, this has nitrogen in it. So I'm like, okay, well, I know nitrogen's diatomic, and I know it's a gas. This also has hydrogen in it. And hydrogen's diatomic, and it's a gas. So formation is, as you're looking at this, this is kind of like almost like a synthesis reaction. But the main caveat is that you have to synthesize it from its elements. This needs to be balanced. So let's see, we can put a 2 here, which gives us 6. So I'll put a 3 in here, 6 hydrogens, and the nitrogen looks good to go. Not only does it have to be from, and let me write, the reactants have to be elements. The other thing is you can only form 1 mole of the compound. So right now we're forming 2 moles. So I'll divide this by 2. There's a 1 here, I'll divide that by 2. So since I'm dividing that by 2, I need to divide everybody by 2. And then my final answer then would be 1/2 N2 gas plus 3/2 H2 gas goes to 1 mole of gaseous ammonia. And again, this would have a 0 value, this would have a 0 value, and all the heat then it's either released or absorbed would be associated with the ammonia. And so that makes it easier for scientists to measure if they kind of think about it this way. So I want to do one more practice writing the standard enthalpy of formation reaction. So let's do this one for the aluminum oxide. And the aluminum oxide is a solid. It's one of the ones that are listed on your table there. And so that's going to be your product. And again, we want it to form from its elemental constituents. So we know that solid aluminum is an element, and the other one will be oxygen gas. Then we'll go about balancing it. I'll put a 3 in front of the oxygen, a 2, that's 6 oxygens, and then 4 aluminum. Finally, we only need to form, when we're writing these, it's required that we only form 1 mole of the product of interest. So let's divide all of the coefficients then by 2. So 4 halves. So when I rewrite this, I'm looking at 2 moles of solid aluminum, 3 halves moles of oxygen gas, going to form 1 mole of solid aluminum oxide. And then that would be your final answer for that one. Alrighty, so on page 11, there's this equation that we're going to use to calculate the enthalpy of a reaction using those formation values that we just discussed. So by the essence of its name, right, it says it's a formation value. And when we think about any kind of reaction, right, the reactants are being destroyed and the products are being formed. So because the products are being formed, I can use these values as is. I don't have to do anything to them. So that's what the first part of this equation is telling us. It's saying sum up everything that's going on with the products and also take the coefficients into account. So since there's 4 nitrous oxides, I'm going to do 4 times the enthalpy value. Then there's a negative sign. So it's products minus reactants. That makes sense because we're not forming our reactants, we're destroying them. And that's why we gotta negate the formation value because we're doing the opposite process. But the same thing, we're gonna sum it up and we're gonna also take the coefficients into account. This is not too bad of a problem. I think the hardest part, for me at least, is keeping track of all the numbers and making sure I don't plug something in incorrectly. But let's do this one together. So we're gonna start with the products, and then in your table, you're gonna look up the specific values. So we have delta H naught of the reaction as a whole is gonna be 4 times the value for NO. So I'm going to do 4 times 91.3 plus 6 times the water value. Make sure you're grabbing, if you're using a bigger table, make sure you're grabbing the water in the correct state. So this is gaseous water. And I usually do like a bigger set of parentheses again because I'm prone to like little errors, mathematical errors, throwing this in my calculator. Minus, so those are my products. I'll grab the value for ammonia, and there's 4 ammonias. So 4 times negative 45.9 plus the oxygen, it's elemental. I don't even need to really look it up on the table because by definition, it's going to have a formation value of 0 because it's in its elemental state. All right, plug this into your calculator, double check it. For this, I got delta H naught of the reaction is equal to negative 902 kilojoules. That negative sign tells me it's an exothermic reaction. And you could take this value and use it in the other problems. You could say, if you knew how much material you had, you could use it to solve for Q, and then plug it into a Q equals ms delta T scenario. So it's not like it's just a standalone type of problem. This delta H naught of the reaction is the same value that you were dealing with in earlier sections. So try the next one. So we're using products minus reactants again to obtain the delta H naught for a reaction. So products, I'm going to look up the aluminum oxide value, and that's going to be times 1 since this has a coefficient of 1 out front. So negative 1,675.7. The iron is in its elemental state. So even though there's 2 irons, it's going to be 2 times 0. So products minus. On the reactant side, we have some elemental aluminum. So again, the value for anything that's elemental is going to be 0. And then the iron oxide value, I'm going to look up. And that is multiplied by 1 since there's only 1 mole of the iron oxide. So when I plug this in, I got a value of negative 851.5 kilojoules.